Thank you. Thank you very much for the invitation. I really enjoyed this conference so far. In fact, I was very happy to see that basically in every talk we had some triangulated category, at least lurking, implicitly somewhere, but prominently. And well, somebody said once that every mathematician has a triangulated category floating around in their ePod. I just haven't noticed it. So I want to show you, make you aware of the fact that operator algebraists are also working with some very prominent tensor triangulated categories since at least in the 80s. They have realized it after 20 years more or less that they were triangulated, but now it's quite active area of research from that point of view too. And quite recently, like infinity category methods have entered the scene too. You will see also why, because as triangulated categories, these are quite defective in some sense. They don't fit the usual frameworks that maybe you are more used to, like topology, algebraic geometry, or representation theory. These categories, they don't have obvious enhancements. That's a big problem. There are many variations on this topic, but I'll give you the most classical and maybe most important family of examples. So we will fix a group G. It will become finite at some point, but let's say in general, it's useful and possible to look at locally compact groups. Hausdorff. And for technical reasons, we will need a second countable. We will see why, I think. But this is already interesting when the group is trivial, okay? The first part of this. And what we have is a category called KKG, which is called, it's the G equivariant Kasparov category. That's from 1988, I think, the equivariant version. The non-equivariant version, the plain version for the trivial group, is like almost 10 years younger. So what is it? Well, the objects, they are, well, let me write the whole thing. They are complex, possibly non-unital, separable G C-star algebras. Now, just a word of warning. Separable here has nothing to do with the separable algebras that we saw in Luca's talk, like having a section of multiplication. No, it's a topological thing. It means there is a dense countable subset. Okay. Non-unital, well, they possibly don't have a 1. Okay. Complex, they are over the complex numbers. C-star algebras. Well, if you don't know, you should think maybe, let's say, so these algebras are all an axiomatic version, so they're all isomorphic. They can be all represented as a like non-closed and closed analytically adjoints subalgebras of some like bounded linear operators over some Hilbert space. Because of the separability hypothesis, you can always take your favorite separable Hilbert space, like L2 of n. But it's an axiomatic framework. They are involutive Banach algebras, satisfying some magic actions. And but people really think of them as algebras of operators on Hilbert spaces made axiomatic. And they have a very old history. And by the way, G just means that this group acts by continuous isomorphisms of such involutive Banach algebras. Okay? Plus continuous, in some sense, G action by isomorphisms of the whole algebraic structure. Alright. So there are variants of this construction nowadays, which also work for abstract associative, possibly non-unital rings. It's called algebraic bivariant K theory, or KK theory, due to 11 continuous and they are stone, and there are variants for locally, complex algebras, all sorts of things. But this is the oldest and most studied family of examples. What are the morphisms? Well, these are these bivariant KK theory groups. If you have two such algebras, then you have, like, people have defined some kind of topological K theory, and then the zeros group, G equivariant, with two inputs. That's called a bivariant G equivariant KK theory, or bivariant K theory, maybe, due to Kasparov. That's what he defined there. And he also defined some kind of intersection product. So it's a very complicated construction, but it gives you a perfect category. Yes?
Is the G action unit term?
Sorry?
Unit term? Does conjugation act on G times A?
Well, it's an action on the algebra, so does unit doesn't act by conjugation. That's by algebra.
So if I take a conjugate of G times X, what does that stand to? Does that commute, like, does it commute with conjugation? Or maybe not.
Oh, the representation, you mean?
Yeah.
On the Hilbert space? No.
On the algebra itself.
I think he's asking if it acts by C-star algebra automorphism.
Yeah.
Okay, yeah.
But not necessarily by conjugation by an element or anything like that.
No, that's one way. Okay. But I think that's
so I'm not going to define these groups, but I'll just tell you, if G is compact, with a finite group, then this, when you plug in, let's say you have a 0 and a 1 group, huh? So a graded version, you plug here the complex numbers with a trivial G action, and you put here any algebra, A. That's some K theory, G equivariant K theory, defined in terms of financial geometry projectives with a G action, blah blah. It's very similar to normal topological K theory. In fact, I should have said examples of algebras here. I forgot. So you can take. I'm gonna finish here. But, if G acts on a locally compact space by homomorphisms, then you can look at the algebra of complex functions vanishing at infinity, and this has an induced G action. So it's going to be an object in here. If assuming the space is second countable, okay, I'm not going to say it anymore. So we have this condition here. And what happens here? So if A is one of these commutative G-sister algebras, that's Segal's equivariant K theory. So it's usually written like this, because it's a homology theory for X. Sense of Atiyah, sorry, this is not from experience that people in the back can't see anything. So this Atiyah Segal's topological K theory of the space. So topologists may be interested in this category also because the commutative G-sister algebras are very interesting. But you may have also actions on matrix algebras and stuff like that. All right, that's more or less the category. I didn't say anything about any details, but I will give you a universal property in a moment. But before that, there's a theorem by Ralph Meyer and Richard Nest, 2006. That's a very influential article, actually, where they show that this is a triangulated category, TT category. Tensor triangulated, symmetric monoidal triangulated with nice properties. So what is the structure? Well, there is a tensor product. That's just sometimes called the minimal completion of the algebraic product of the complex numbers with a diagonal G action. But you could also take another completion called the maximal one. These are usual tensor products of sister algebras with a diagonal G action. The tensor unit is just the complex numbers with trivial action as used for K theory here. And if you know a bit of this, you know that the endomorphism ring, so in fact, the graded endomorphism ring of the tensor unit is going to be the complex representation ring of the group if it's compact. I always can say if it's compact, otherwise that's not clear what that should mean. But that's the complex representation ring. And then, well, you have a convertible bot element. You have, this is in degree 0, you have nothing in degree 1, and then it's 2 periodic. In fact, the suspension is 2 periodic. So the suspension is given by tensoring with the interval, smashing in the interval in terms of algebras. So these real numbers with a trivial action, you tensor it in this sense with something, and this is 2 periodic. It's a form of Bott periodicity. Okay. And in fact, the shortest proof I've ever seen of Bott periodicity involves noncommutative sister algebras. There's no group for that, huh? The trivial group case. And you can go from the definition of sister algebra to the proof of Bott periodicity for topological K theory in a short few nice pages. I think Guillermo Cortinas has a nice lecture notes about that. What else? Well, what are the triangles here? Triangles are some kind of extensions of algebras or Cooper sequences, depending how you want to see them. So distinguished triangles. They are it's called semi-split extensions of such algebras. So this means you have you have some ideal. Remember, these are non-unital algebras, so you can an ideal closed ideal, two-sided ideal is again an algebra, and a quotient here. Then these are equivariant morphisms of such algebras. Then you have some. You assume that there is some nice linear, completely positive, contractive splitting. Okay, it's a condition. If the algebras are commutative, for example, it's always the case. And then you have some. In KK theory, well, you can put it here or here by Bott periodicity, doesn't matter. People put it here usually. In KK theory, you always have a map like this, and it makes it into a triangle. These are the triangles, all isomorphic and stuff like that. Or, if you prefer, you have a non-commutative version of Cooper sequences. And that's an exercise for you to figure out what it means for non-commutative, for a morphism of general such algebras to construct the mapping cone, which is actually more like a fiber, because everything is reversed by the C0 construction. And then you do a pullback, some kind of cone, evaluate the kernel, that's the same. So anyway, and then some Cooper sequences are kind of equivalent to that in this category. So it's, in some sense, people have been trying to redo what Spain and White had been a long time ago to construct the first triangulated structures. So it works. As I said, this has been the reason for lots of people in this subject to actually learn about triangulated categories. But also, if you, so let's say, I want to give you a universal property for this category here, which maybe talks more to people who don't care about operator algebras, things like that. What is this, the deal with this thing? So that's another theorem I want to mention. That's due to many people, but the first such thing is due to Nigel Higson, long time ago. But then Thomson and then Ralph Meyer have done the equivariant version. I don't know in which years. And what does it say? So there is a canonical functor from separable sister algebras into KKG, which is the identity on objects. Okay. And does something and constructs some canonical cycles out of morphisms. And his initial among functors which are well, let's say split exact. There are many variants, but this is the simplest one, I think. Split exact. I will explain each word. Stable, and we should maybe add KG stable. It's not the same sense of stable as topologist practice. And you also want maybe homotopy invariant. Then what do you want? You want functors into some additive category, just additive. So you can express these properties to an additive category. So what are these? Split exact means if you have an extension of the G-sister algebras which happens to be split by an algebra morphism, and then you go into an additive context, you want that the split is a direct sum, okay? This goes to a direct sum of you know, A and B, A and C, okay? Splits in the middle. Because then if you can do additive stuff, then you can also switch that, right? You can imagine how it works, right? You want these three maps to induce a direct sum diagram. This is something that operator algebraists want to do all the time. They want to construct, so it corresponds a little to Morita invariants in the sense of matrix algebras. So if you have a sister algebra, you often want to take matrices with entries in there, and you want to do it a lot with bigger and bigger matrices, and then you want to complete and you get another big non-unital sister algebra, and you always want to write down matrices. So you want, and then K-theory, for example, logical K-theory doesn't see the difference between the algebra itself and this big matrix algebra. And then you want to take into consideration all possible group actions on the matrix algebra. So what you do in practice is you consider some non-zero Hilbert spaces, and then you may maybe include them as a direct sum in a bigger one. These are G Hilbert spaces. And then you can look at so-called compact operators on them, which are some kind of completion of all the possible finite matrices of finite rank operators. You construct on them. So if you don't know what they are, doesn't matter. But so this you have an induced morphism of algebras like this, namely a compact operator on H, some kind of nice infinite matrix. Can be extended by 0 to act on the bigger Hilbert space, and there are induced G actions here and here. And then if you tensor that with any G-sister algebra A, you want that to become invertible. Think, for example, if H is the complex numbers, you will have a copy of A goes into, I don't know, if H prime is just a n times n complex matrix, C to the n, that's n times n complex matrices, and then you will have A goes into n times n matrices over A with some action. You want that to be invertible, okay? But it's much more general. So this goes to an ISO for every A, every such H and H prime. It's called a stability for compact operators. Yeah.
Is G supposed to be invoked in the left-hand side of that canonical map in some way?
G?
At the top. Is G on the left?
Sorry. Oh my god, I thought this C was a G.
Thank you.
Apologies. Yeah, of course. Sorry. The objects are the same.
Good, thank you.
Thank you very much. Yes, sorry. You have an action everywhere. I won't forget. Homotopy invariance, well, it means you have every A goes into interval times A, constant function times A, and you want this to go to an isomorphism. Okay, so this is the natural interval you can do homotopy within there. You want that the function to be invariant with respect to this homotopy. So this is a universal property, but there are some miracles here. Let me stress the miracles, because it is not at all clear why the universal such function to an additive category should have a value which is a triangulated category, right? So it's crazy how miracle one, like say additive plus this split exactness actually imply that in the universal guy you have a triangulated category and this semi-split exactness where many more extensions go to triangles. In fact, almost all the extensions we can write down. So that's very nice. And the second miracle, which I mentioned for general culture, because it shocks people, is that homotopy invariant is automatic, follows on the other two. Homotopy invariant is redundant. Well, I think you have to replace it with a, I'm not sure, but with the zero algebra goes to zero, something. And very pretty accident. So the thing is, if you don't know about these kind of tricks, like if you can write down matrices and you are in a tensor algebra, you can do things like you can interpolate between elements in a very continuous way, and then suddenly you can do homotopy theory by rotating things and so on. And you know, if you can always go to matrix algebra in an unpunished way, then you automatically get homotopy there. So that's a theorem by Nigel Hickson, I think. Anyway, so you can imagine if you want to construct a similar bivariant K-theory for, I don't know, rings or something else, you will have a similar universal property. That will be the goal, right? You want some kind of, I don't know, polynomial homotopy invariance. You want some kind of K-theory at the heart of it, like here. Homotopy invariant algebraic K-theory. And then you want some kind of extensions to go to triangles. No, that's what you expect, and that's what you get. All right, so that's the main players of this talk. Let me also mention that another miracle that happens, maybe miracle 3, is that this category has some infinite coproducts, has all countable AKG, has countable coproducts. So, no more than that. There are no non-trivial uncountable ones. There are no infinite products. But there are countable coproducts. Because essentially there is a construction called the direct sum of sister algebras. It's some nice algebra infinite product. And if each factor is separable, the direct sum is separable, so it just is there. And by magic it happens to become a coproduct in there. This is kind of the source of the problems. It will show that it means that the category KKG is neither big enough to do some stuff, but it's too big to do other stuff. Unfortunately. Why is, I didn't say why separable, but essentially because to construct these mysterious abelian groups, you need a lot of analysis. At some point you need, at several points you need a separate group. Otherwise things just don't work technically. Unfortunately. There's no conceptual reason, it's just a very annoying technical reason. All right. So, why study this category? Well, I'll give you one motivation. There are many, but maybe the most flashy for people who are interested in this operator algebras and in group actions is the bound-con conjecture. So, the bound-con conjecture is famously hard to explain. When I was a PhD student, I saw people give talks and say, oh, I cannot possibly explain what it is about in less than 1 hour, so we're just assuming you know what it means. But thanks to Meyer and Nest, using tensor triangulated categories, maybe these ones, you can explain what it is in 5 minutes. I will do it.
I don't have the gong now, but...
So it's actually a theorem. Oh, yeah, no, I'm stressing the thing is, so there was a bound-con conjecture before these categories, but people have found it more and more convenient to reformulate everything about that in terms of KK theory. And the ultimate reformulation of the conjecture is it fits in that square there. Let's see how cleverly I can present it. So you can define something called CI for compactly induced. So this is basically, now we have a tensor triangulated category with some kind of infinite coproducts, so we can take localizing subcategories generated by the stuff. So I take the, in a countable sense, but still. Localizing subcategory generated by, well, I take everything which is induced by some compact subgroup. H is a compact subgroup of G. And then there is some kind of easily described induction function, which is, you can kind of guess it here. You have some tensor with something, some form of G and then over H, induced induction. Of everything you can see that has an H action, all right? That's inside KKG, so you have an inclusion in KKG by definition, full subcategory. Nice localizing tensor ideal, in fact. And the theorem of Mayonnaise is that this has a right adjoint. And in fact, the right orthogonal is also a localizing tensor ideal. Okay, so you have a gluing triangle. And that's, well, I'm spoiling the punchline. So this has a right adjoint.
So the union, I assume, is over like groups, subgroups that are different from G.
Compact. This statement, so the statement of bound conjecture is kind of trivial if G is compact. If G is discrete and infinite, then it's very interesting already. But if it's, let's say, finite group, then it's not compact. So this inclusion has a right adjoint. Let's call it A goes to A tilde, or lack of, because that's what we call it. So there is a counulative adjunction. Like this. All right. So you go back, you go down into this compactly induced stuff. You re-include it here, and you have a counulative adjunction. And if you apply, look at this, and then you apply the ordinary K theory of this ordinary system algebra. So you can do a cross product. It's called reduced cross product because you have to complete it to get a system algebra in a certain way, but it's just some kind of, you implement the action inside a bigger algebra. You can apply to this one, and then you can apply it, you can do the same thing. This is induced by epsilon. You can do the same thing with A. And this is the so-called bound cone assembly map. Which was defined a long time before. Bound cone assembly map. So that's a theorem. I'm not going to tell you what the reduced cross product is, but you can imagine if you know an algebraic version of this, it's just some like minimal completion you can do to get a sister algebra. So remark is the theorem, and the remark is that the famous bound cone conjecture for the group G, because every group has its statement, and for the coefficients in A, so with coefficients in A, that's what people say, holds by definition, or by this theorem before, holds if and only if this map is invertible. Okay? So this map induced by the counit is an isomorphism in ordinary topological case. And if you ask yourself why do people care about this, I'll give you the example where A is the trivial G-sister algebra. Remark 2. So for A equals the complex numbers with trivial action, this reduced cross product is just sometimes called, usually called the reduced group sister algebra of G, which is a way of embedding G as a unitary elements of some sister algebra in a universal, in a minimal way. Sorry. And people have been trying to compute the K0 of this, to prove things like, for example, the rational group algebra of an infinite group has no non-trivial idempotent and stuff like that. you look at K0 of this thing, and the injectivity of this map already proves a conjectural idempotence, for example. There are many, many consequences. So it's a very important, very much studied thing. And now, thanks to the magic of tensor triangulated categories, we all know what it's about. I hope it was more or less understandable even though I haven't defined this cross product. So, at the time, when the time this article came out, I was in my thesis, and so I was like, oh, new triangulated categories. Tensor triangulated categories, let's try to do something with it. And Balmer had just, or shortly before, had introduced the spectrum. So let's look at the spectrum of AKG. What can you say? I mean, is it interesting? And so I proved something. I'm going to call it theorem, but actually it's very easy. In my thesis, I could give the whole proof, because every talk needs a proof, right? But I'll give another one. So the thing is that, in fact, this map here, epsilon A, say, is epsilon for all A is invertible, which means that everything is completely induced as soon as the following map is surjective. So what you do is, well, you look at all the compact subgroups of G, you look at the Balmer spectrum of this, well, it happens to have a countable coproduct, but it's essentially small, right? It's essentially small tensor triangulated category, so why not? And then you have obvious restriction functors from G to H, which induce maps in spectra, because they are tensor triangulated functors, and you go to the spectrum of KKG. So it's easy to see that because essentially you have some nice, I will call them like finite, this is a finite localization that you get here with this subcategory. It's smashing, and so essentially you look at the cone of this map, which is in the right orthogonal of this, which happens to be everything which restricts to 0 on compact subgroups. And then you have some nice trick that says an object is tensor nilpotent if and only if it belongs to every tensor triangular prime. But then the cone of this is tensor idempotent, so it's going to be 0. And so if you have this, if all the primes come from compact subgroups, and an object restricts to 0 to all of them, and all these categories, it's an easy proof. And what makes this interesting at first is that this is cool because all the cases of the Banach conjecture that have been proved, or all the families of groups which is known, they actually prove this, that this map is invertible before applying the cross product in theory. So virtually all cases of one con known throughout the years hold because people can show essentially that, well, it's a bit more complicated, but because this map is an algebra, okay? Cool, so that was very exciting. But actually, it turns out that this is almost completely useless because, so unfortunately, so the problem, there are virtually no methods for computing such spectra or such categories. Because as we have seen maybe also throughout this conference, usually what you do is, if you want to do some tensor triangular geometry and study this kind of spaces, you need compact rigid objects in a big rigid complicated tensor triangular category, like all the ones that came up in previous talks were that kind. So the methods for studying the spectrum of some category work best, or usually need, not all, the more advanced ones, need some T which is big and nice. So you need in particular all coproducts, so to have a nice representability theorems and stuff like that. Stratification, all this stuff needs lots of technical things which only work if you have arbitrary coproducts. And then you look at the spectrum of the compacts, which should be also the same as the dualizable. Okay, and so you have a nice small GT category inside a big nice one, and then you can do lots of stuff. But for such guys, can't do anything at all, almost nothing.
Do you know what the compacts are in these KKGs?
No, I know if I look at the, I will say in a moment, you can look at inside here at slightly, maybe a lot smaller categories, and they have nice compacts, which are also rigid. But you have to restrict attention. I will say it in a moment. So the thing is, one has to be more modest in some sense. And you will see that in fact, people, even people who do Hong conjecture and so on, are not using the whole KKG. They're using smaller parts. Nice. Then you can look at smaller categories which have nicer properties. Yes?
When you mean spectrum, do you look at thick tensor ideals, or are you also looking at those which are closed under the countable coproduct?
That's a very good question. I want to say more about that. I just consider them as, they classify the thick radical tensor ideals. Just the usual one. I forget that there are countable coproducts. Maybe one shouldn't. So
I think this in log, you did mean that you close on a countable coproduct.
yes, yes. So in order to have this conclusion, this result, I need, the whole category, because I'm considering objects here which are certainly not compact and certainly not rigid. So no. But and they're supported. By the end of the talk, I hope I will give you a version of this, which has the same conclusion, but which the hypothesis says that you have a surjectivity where here you have a much nicer, smaller category here too, and the spectrum is one that takes this infinite coproduct into consideration. And so there is hope of computing those things. But first I want to show what kind of stuff you get when you try to do nicer things. So let's say for a moment, let's try to be more modest. So first of all, we restrict to, for the moment, G compact, or even finite. Or if it's infinite, it's going to be discrete. But let's forget the infinite one for now. So what we do, now let's assume that G is compact. Then I can look inside here at categories which have a nice set of generators. Because one of the problems is that there are just too many GCs algebras. Even for a trivial group, just too many. There is no nice known set of generators here, in the triangular sense, in any way. But you can just do it by, artificially. So people often study something called the bootstrap categories. So this is the best version here. So it's the localizing subcategory generated by some nice things. And here you take all the induced actions from H to G on matrix algebras of some sort. So you have some action alpha. So here you have H in G, any subgroup of the compact group G, and alpha is G acting on this matrix algebra. H acting in some way, and then you induce up. And these are called elementary GC algebras. They are very nice, as nice as you can get. They are in general non-commutative, and they generate a nice tensor triangulated subcategory. And inside here, as topologists, maybe you want to look at something a bit easier, something that we call cell G. This is the same thing, but you only take the commutative ones. So those in the end which have the form complex functions on G modulo H. Okay. for all H in G. This is the same, by the way, this is the same as inducing from H to G the trivial algebra, with trivial H algebra. So you see these are special cases of this, but they are all commutative. There is no zero here because G mod H is a complex space. These are just complex functions with induced G action. These are the orbits, right? So H, let's say, well, closed, has to be compact. So these two here have nice properties. They are rigidly compactly generated in a countable sense. Compactly generated into categories in a countable sense. So this is implicit in the work of Meyer and Nest, and then I have elaborated a bit on that. So you can do things like Brown representability for cohomological functors, but not for homological ones. You can do some stuff. You have a nice set of compact and rigid generators, which somehow are those which have some finite condition on the K theory and stuff like that. So that's good. So you can look at the spectrum of the compacts in there, okay, and see what you get. Now, note that this is the analog of the stable homotopic category of genuine G spectra, right? Because the generators are the same, now they're duals of the orbits, and you make them into a tensor triangulated category in some way. And in fact, the suspension spectra they all get inverted in here. But then you have what releases because you have topological case. Anyway, what happens if you look at try to compute with these things? Well, something more is known. So I'll give you the state of the art, and then I'll tell you what this could be good for. It's been a long time. So it took people in working in this subject around 20 years to realize they had so around 10 years to realize that KT3 was a category, which is a bit strange, but they had something called the intersection product, the Kasparov intersection product, which was a mixture of composition and the tensor product functor. They didn't realize it, The grading was inside in the machinery, the DMC was suspension. And now they are starting to realize that they need a nice triangulated category. So you need maybe an enhancement, nice set of generators and so on. They're realizing that without that, life is hard. And this is one solution you can do. So maybe let me just mention, I don't think I have time, but let me mention quickly, with Rathmeyer and Heath Emerson, we have proved that in the bootstrap category, in the boot G, you have inside there basically all the nice GC structures. Those with underlying type 1 structure, if you know what I mean. It's the same thing actually. And the cell G contains, for example, all the commutative ones that come from countable GCW complexes. So if you want to do topology, cell G is good enough. Okay? Now, I give you the state of the art of tensor triangular geometry in this context. And it's not very advanced, but it's the best we can do for now. The theorem by myself and Rathmeyer last year actually, says that if G is a cyclic of prime order, then it's very nice. Then the canonical comparison map defined by Urbano in full generality that goes from the spectrum to the Zariski spectrum of the endomorphism ring of the unit, which remember it's just a complex representation ring in this case. And here I put the category of stellar G-sister algebras, and I take the complex ones. And this is a homeomorphism. Okay. Now, this is the best we can do, but it hints at, so gives us some hope. I'll tell you why. First, I want to give you a sketch of the proof, because if you know how the proof goes for a stable homotopic category of G spectra, it's the same proof, but with a very different ingredient, because there is a crucial difference in the structure of these categories.
What is the subscript on cell
C for compact, sorry.
Okay.
The compact objects, or rigid, or dualizer. So we are being reasonable. We are looking at, rigid compact objects inside a nice category. So how does that work? So the idea of the proof. So the case for the trivial group I was known since my thesis, and it's actually very easy. Will be used here. This is way more difficult, and these methods stop here. I mean, beyond these groups, we think we have to find something else, and I will tell you what we think might work. So the idea is like this. So remember that the representation ring for in this case is just the group ring of the dual, because it's an abelian finite group, but the dual is just again CP, right? So that's just a polynomial ring in one variable modulo x to the p minus 1. Okay. So in fact, we first we know that this is surjective by some abstract nonsense, and so we have a fibering of this space over that. So let's look at this space. Okay, that's well known to have a very classical thing. You have so this ring here. So you can so this x to the p minus 1 has two irreducible factors, right? X minus 1 and the cyclotomic polynomial. So you can mod them out. Mod x minus 1, or you can do mod the other factor, which is 1 plus x squared until x to the p minus 1, because p is prime. So here you get z, and here you get z adjoint a primitive pth root of unity, which maybe I'll write like this. Pth root of unity. And on the level of Zariski spectra, it says that this is the spectra of these two are the images here are the two irreducible components. Okay, they are fine. The maps are injective, and they glue at exactly one point. So this point is a unique close point over P. So on spec, this is a disjoint union as sets between spec Z and spec of this. That's another dedicating domain. So two lines somehow. And you get so union except for one point for the unique closed point over P, which lies in the image of both. So you realize if you invert P, for example here, you get rid of the redundancy and you get that disjoint union of sets. Okay? That's what we're going to do. And then we try to copy this at the level of categories. Okay, now copy this for cell G. Now what we do is cell G, well, you can restrict to the trivial subgroup. That's a nice tensor triangulated function. So let's look at coproducts, okay? That works because it has a left and right adjoint, which is induction. And so it induces a map backwards on spectra, on boundary spectra. Here you can do something else. You can localize and kill. So now this, remember, this has two generators because it's a secret group, so of prime order. So this is generated by the tensor unit, which is the functions on G mod G, and then the functions on G, which is functions on G mod the trivial subgroup. Okay, the two orbits. So if you kill the localized the fixed subcategory generated by C of G, let's call this the resulting quotient Q. Then you have a nice tensor triangulated category generated by its tensor unit. Now let's look what happens at the level of spectra. This is what we want. This is a spectrum of this other one. This is spectrum of the base one for the trivial group. And then you have these comparison maps, which are natural. So if you look at what happens to the endomorphism rings of the unit, here you have the integers, spec Z. So you have this picture again on level spectra, spec RG. This is this. In fact, what turns out is that this is this ring here with P inverted magically. So this is the crucial part of this construction. To show this, so this is the endomorphism ring of this category Q. But we have to compute that, okay? It's completely non-obvious. This computation needs a very special result, some kind of universal coefficient theorem, due to a student of Meyer, Manuel Köhler, which only holds for cyclic groups of prime order. So it's a very particular computation. So this, I'm not going to go into details, but that's a hard part of the proof to show that we get this ring here, which is exactly what we need because in this case nature is kind. So we have inverted P, so we get a disjoint. This is a disjoint union as sets. Disjoint union decomposition of sets. And now I know that this is also a disjoint union of sets by general techniques of tensor triangular geometry. I'm just going to tell quickly because there is no time, but the thing is, this algebra C of G, so this is a set of tensor primes. They either contain C of G or not. Those which contain C of G are in the image of that by construction. Those that do not contain C of G are in the support of C of G. But the support of C of G is exactly the image of this, because this has an adjoint, which is induction, and which sends a tensor unit to C of G, which is a separable, in the other sense, sense of Lucas talk, a separable ring in a tensor triangular category. So you have all this abstract nonsense applies here, and this is a nice disjoint union decomposition. So it's enough to show that this is bijective, this is bijective, to have this is bijective. Actually, injectivity is the hard part. This it is because you can compute everything in this category by the classical Rosenberg-Choquet universal coefficient theorem in the 80s. Just like we use the generalization by Manuel Köhler to compute this. But why is this bijective? That's another abstract piece of tensor triangular geometry due to myself and Don Stanley, which says, oh, if you have any tensor triangular category which is generated by its tensor unit, and whose graded endomorphism ring is regular and Noetherian, well, we have both periodicity. This is in degree 0, there's nothing in degree 1, we have completed that too. That's regular and Noetherian. So localization of a Dedekind domain. So yeah, so that's by abstract by myself and Stanley. We have this. This is easier. So this is bijective. Now, if you try to go beyond city groups, it doesn't work. Okay. Yeah?
I might have missed it, but I think you didn't finish the statement. You started something And the morphism ring is regular Noetherian.
Yes, sorry, I'm running out of time. I want to say that there is an abstract criterion. So these maps, vertical maps, always exist. If you have a tensor triangular category, you can map the triangular spectrum to the Zariski spectrum of the endomorphism ring of 1. Provided it's under some very mild hypothesis, it's always a surjection. That applies here, essentially because the endomorphism ring is Noetherian. But why is it injected? In general, it's not injected. In a stable homotopy theory, it's far from injected, okay? Even for a trivial group. But if you're lucky and your category is generated by the tensor unit, and the graded endomorphism ring is regular in some sense, and Noetherian, then, for example, if it's 2 periodic, considered in even degrees, and in degrees you have a regular Noetherian ring, then you can absolutely prove that you always have a bijection in the comparison. It's an abstract criterion, even if you don't know anything more about Q. Okay? You have to compute this ring, and we did. So that's the proof. Now, the reason this might be useful is that there is another theorem by myself and Ruben Martos, who used to be in Copenhagen until very recently, which says the covering criterion for a theorem to obtain bound con, which is still there, this theorem here, also holds with, well, you would replace kk of something with cell of something, like in here, these cellular objects, and you replace the usual Balmer spectrum with something which takes into consideration the infinite countable coproducts. And then the theorem is not obvious because you really have to go into how Meyer and Nest construct their assembly map and so on. But it's true, so you don't need to look at the whole category. And conjecturally, thus, at least for G finite, sorry, this only holds for G discrete, but it's enough to have all the bound con, original bound con is for discrete countable groups. So if G is finite, we think that this spectrum of boot G should be the same as the usual spectrum of the compacts, because there should be some stratification here in the big one, some countable stratification, as in Natalia's talk. But we haven't proved that yet. But we think that's just a conjecture. It's true for the trivial group, so maybe it's true for finite group. Okay, so in some sense we can salvage this hopeless, useless criterion for bound con. But we need to be able to compute this, well, at least more of this spectra for the compact widgets in the, sorry, I would boot, should cell, but they're the same for many small groups. So the last thing I want to say in the last minutes is that how to go beyond the cyclic groups. Well, very recently, people have started to introduce enhancements for KPG, even for G infinite but discrete. So for G discrete, maybe infinite. So I'll just give you the name. This is work by Ulrich Bunke, Engel, and Land. So this is a long preprint from 2021. They have a bigger version, let's say KKG tilde, which is a nice, presentably symmetric monoidal infinity category, whatever you want. One of these nice big one, stable homotopy theories, such that the compact objects are KKG. And it sits nicely as a full tensor triangulated subcategory inside. That's a non-obvious result. So the construction is kind of simple-minded here, but the fact that this sits inside here very nicely is non-obvious. And they extend the induction, restriction, all this contrariety. They do a lot of work. They study also the assembly map and so on, and they haven't looked at the spectrum, but I think now that you have, and this has a nice universal property which mimics the one I gave you before. So what I suspect, I was talking about this with somebody in the audience yesterday, but I suspect that now that everything lives in the same world, like genuine G spectra and this KQ theory, you can start to compare them. You can construct functions that relate them, and these should be closely related to the module category of KUG. So KUG is the genuine equivariant complex theory spectrum, right? And it's easier to get results like computing spectrum. And then if you restrict inside here to stuff generated by the usual orbits, you should be able to do the same thing, especially if you can compare in the same world the two categories, this one and genuine spectrum. None of this is written, or it's just the hope that soon there will be breakthrough. And it's also an invitation to all young, young in your sense, anybody who feels young and needs a challenge to actually go and study these categories, because there is a lot of potential applications and big results which might just fall out of general infinity constructions. So good luck. Thanks.